Hello friends, today let's look at the algorithm of checking if a binary tree is height balanced or not. This algorithm runs in order of n time. So let's first define what is a height balanced tree. A binary tree is called height balanced tree if it satisfies the following condition. For all nodes of the tree, the absolute difference between heights of left subtree and that of right subtree should not be greater than 1. Let's look at some examples. For tree T1, there is only one node, node 5. The left subtree is null, therefore the height of left subtree is 0. The right subtree is also null and the height of right subtree is 0. Therefore, the difference between left subtree and right subtree heights is 0, right? This difference is not greater than 1 and therefore this tree T1 is a height balanced tree. Let's look at tree T2. Note that for node 4, left subtree and right subtree are null. Therefore, height of left subtree and right subtree is 0. Now, for node 5, height of left subtree is 1 and that of right subtree is 0. So, the difference between height of left subtree and right subtree is 1, which is not greater than 1, and therefore this tree T2 is also a height balanced tree. Now, for tree T3, the height of left subtree when we look at node 5 is 2 and height of right subtree is 0. Now, this difference of heights, that is 2, is greater than 1. So, in tree T3, node 5 violates the condition for height balance and therefore this tree is not a height balanced tree. Now, for tree T4, you can observe that all the nodes satisfy the condition for height balance and therefore this tree is a height balanced tree. For tree T5, if you look at node 5, the height of left subtree is 2, right? 1 and 2. And height of right subtree is 0 because right subtree is null. Therefore, this particular node violates the condition for height balance and therefore the tree T5 is not a height balanced tree. Note that all the nodes of a tree should satisfy the condition for height balance. The condition is that the difference of heights between left subtree and right subtree should not be greater than 1. Now let's try to solve this problem in order of n time. So in this algorithm, which is basically a modified post order traversal, for a node n, we first check if the left subtree is height balanced. That is, we check if all the nodes in the left subtree of node n satisfy the condition for height balance. If the left subtree is height balanced, then we are returning its height to the calling function, right? Otherwise, we return -1. Similarly, in step number 2, we check if the right subtree is height balanced. If it is, then we return its height to node n or calling function. Otherwise, we return -1. Now, once we conclude that the left subtree of node n and right subtree are height balanced, in step number 3, we check if the tree is height balanced at the node n itself. How do we do that? We check the difference between heights of left and right subtrees. If this difference is less than or equal to 1, then we say that the tree is height balanced at the node n itself. Now note that in step number 3, we require the height of left and right subtrees, and we get that from step number 1 and step number 2 respectively. In step number 1 and in step number 2, we are returning the heights of left subtree and right subtree if they are height balanced. So in step number 3, once we conclude that the tree is height balanced at the node n itself, we return 1 plus maximum of height of left subtree, height of right subtree, right? This is basically the height of tree rooted at node n. If the tree rooted at node n is not height balanced, then we return -1. Notice that this is nothing but a modified post order traversal where we are first checking if the left subtree is height balanced, then we are checking if the right subtree is height balanced, and finally at the node n itself we are checking if the tree is height balanced. The base case for this recursive algorithm is that if node n is null, then the tree rooted at node n is height balanced and we return 0 because 0 is the height of null tree. Let's look at an example now. For this tree, let's say we are looking at this particular node n. So node n is node 0. The first step of the algorithm is we first check if left subtree is height balanced. Left subtree for this node is null tree, right? Now the base case comes into play where if node n is null, then the tree rooted at node n is height balanced and we return 0. So this particular node returns 0 here, right? Note that this is null tree and it is height balanced, therefore it returns its height to calling function. Similarly, the right subtree for node 0 is null tree. This tree also returns 0 here. Now in step number 3, we check if the tree is height balanced at the node n itself. And for checking that, what we do is we check the difference of heights of left subtree and right subtree. The difference comes out to be 0. Therefore, we conclude that the tree rooted at node 0 is height balanced and we return 1 plus maximum of height of left subtree and height of right subtree. That is 1 plus maximum of 0, 0. So overall, this node 0 returns 1 to calling function. Similarly, you can verify that this node 2 returns 1 to calling function. Now at node 1, we again check the difference of heights of left subtree and right subtree. The difference is 0. Therefore, we conclude that the tree is height balanced at node 1. Once we conclude that, we return 1 plus maximum of 1, 1, which is 2. So 2 is returned to calling function. Similarly, you can verify that this node 5 returns 2 to calling function. Finally, at node 3, what we do is we check the difference of 2 and 2, which is height of left subtree and right subtree. The difference is less than 1. Therefore, the tree rooted at node 3 is height balanced and we return 1 plus maximum of 2, 2, which is 2. So overall, we return 3 from this calling function and this 3 is interpreted as true. So this was kind of an abstract run through the algorithm. Let's look at the concrete algorithm and run it on this particular example. So the subroutine check balance takes argument as node n. The base case is if node n is null, return 0. We call this step number 1. If node n is not null, then we first check if left subtree is height balanced. If the left subtree is not height balanced, it will return -1 and will return -1 overall to indicate that the tree rooted at node n is not height balanced. If the left subtree for node n is height balanced, then we check if the right subtree for node n is height balanced. If the right subtree is not height balanced, then it will return -1 and overall will return -1 to indicate that the tree rooted at node n is not height balanced. Now, if the left subtree and right subtree both are height balanced, then we check the difference between height of left subtree and height of right subtree. If it is greater than 1, then we return -1 to indicate that the tree rooted at node n is not height balanced. If the difference between height of left subtree and height of right subtree is not greater than 1, then we return the height of tree rooted at node n. To do that, we simply do this computation, right? 1 plus maximum of height of left subtree, height of right subtree. Let's run this algorithm for this particular tree. For ease of explanation, I'll call this block as step number 1, then this block as step number 2, then this block as step number 3, step number 4 and return statement as step number 5. The first call to subroutine check balance is made with root node, which is node 3. So this is very first call to subroutine check balance. The first step, which is a base case, will have no effect in this case because node 3 is not null node. In the second step, a recursive call is made to check if the left subtree, which starts from node 1, is height balanced. So while checking if the subtree rooted at node 1 is height balanced or not, the first step will have no effect because it is the base case. In the second step, we check if the left subtree, which is rooted at node 0, is height balanced. In this call sequence where current node is 0, the first step will have no effect. In the second step, we check if the left subtree is height balanced. In this case, the left subtree would be null tree, right? So in this call sequence where the current node n is null, the first step, which is base case, comes into play. Note that in the first step, we check if n is null. If it is null, we return 0. So this particular call sequence returns 0 here, right? Now we are back in the call sequence where current node n is node 0. In the third step, we again make a recursive call to check if the right subtree is height balanced or not. Now here, the right subtree for node 0 is null tree, right? Same as step number 2, it will again return 0. So step number 3 basically makes a recursive call to check if right subtree is balanced. Same as step number 2, it will again return 0. So the right subtree is height balanced. Once the step number 3 returns, in step number 4, we check the difference between height of left subtree and right subtree. The difference between height of left subtree and right subtree would be 0 in this case, right? Which is not greater than 1. So the control drops to step number 5. In step number 5, what we do is we return 1 plus maximum of 0, 0, right? So this 0 is returned from step number 2 and this 0 is returned from step number 3. So overall, from the call sequence where current node n is node 0, we are returning 1 plus maximum of 0, 0, which is 1. So this call sequence returns 1 here, right? I'll erase the completed call sequence for more space. Now we are back in the call sequence where current node n is node 1 and step number 2 has returned 1. Now in step number 3, we again make a recursive call to check if right subtree is height balanced or not. Note that we are currently looking at node 1. The right subtree starts from node 0 and we make a recursive call to check if right subtree is height balanced or not. Right subtree starts from node 2. Now you should be able to verify that very similar to step number 2, this step, that is step number 3, will also return 1 to indicate that the tree rooted at node 2 is also height balanced. So step number 3 will also return 1. So after completion of step number 3, what we have is height of right subtree stored as 1, right? Note that in step number 3, we are storing the height of right subtree, right? And in step number 2, we also have stored the height of left subtree. So left subtree height is also 1, right? Which was returned from step number 2. Now in step number 4, we check the difference of left height and right height. The difference is 0, which is not greater than 1. Therefore, the control drops to step number 5. In step number 4, we have concluded that the tree rooted at node 1 is height balanced. In step number 5, what we do is we return 1 plus maximum of left height and right height. So maximum of 1, 1. This is basically the height of tree rooted at node 1. So overall, what we are doing is from the call sequence where current node is node 1, we are returning 1 plus 1, that is 2, right? I'll erase the completed call sequence now. Now we are back in the call sequence where current node n is node 3 and step number 2 has returned 2 to indicate that the left subtree, which is rooted at node 1, is height balanced. Now in step number 3, a recursive call is made with current node as node 5 to check if the subtree rooted at node 5 is height balanced or not. So in this recursive call sequence where current node is node 5, the first step will have no effect. In the second step, we make a recursive call to check if the left subtree is height balanced or not. The left subtree for node 5 is rooted at node 4. Therefore, recursive call is made with current node n as node 4. Now you should be able to confirm that this step number 2 will return the height of tree rooted at node 4, which is 2. This is because the tree rooted at node 4 is height balanced and it returns its height to the calling function. So step number 2 will return 2, right? Now remember that we are in the call sequence where current node is node 5. The third step checks if the right subtree is height balanced or not. The right subtree is null, right? So n is null. A recursive call is made to check if this subtree is height balanced or not. As we have previously seen in this video, when the current node n is null, we return 0 to indicate that the null tree is height balanced, and it returns its height, that is 0, to the calling function. So third step returns 0. Now in the fourth step, what we do is we check if the tree rooted at node 5, that is the current node, is height balanced or not. To do that, we take the absolute difference between left height and right height, right? So left height returned is 2, which is in step number 2, and right height returned in step number 3 is 0. So the absolute difference is 2, which is greater than 1. Now observe that in step number 4, when the absolute difference between left height and right height is greater than 1, we return -1 to indicate that the tree which is rooted at node n is not height balanced. So the tree rooted at current node, which is node 5, is not height balanced, and it returns -1 here to the calling function. I'll erase the completed call sequence. Now when step number 3 returns -1, what we do is we return -1 from this call sequence as well to indicate that the tree is not height balanced. So in step number 3 itself, when this part returns -1, we return -1. So overall, from the call sequence where the current node is node 3, value of -1 is returned, which is interpreted as false, right? So the tree rooted at node 3 is not height balanced. I hope the intuition behind this algorithm is clear now. Because this is modified post-order traversal, both time and space complexity of this algorithm is order of n. You can check out our website www.ideserve.co.in for more such questions. Thank you and cheers.